but just in case someone from outside is visiting, Sunanda Banerjee is a senior professor at SINP, and he has previously worked with TIFR, Fermilab, and University of Wisconsin-Madison, and he has been with CMS since 1993. So I'll just let you start whenever you're ready. And yes, I see your slides, but I don't hear you yet.
Can you hear me now?
Yes.
Just 1 minute more. 1 more minute. Okay. I took the liberty, okay, of changing the title of my talk. Okay, I'm not talking about Indian contribution to CMS. Okay, I mean, I basically try to talk about CMS detector simulation and where India fits in there. So it is a little bit more okay than just the Indian participation in the CMS simulation. Now, many of you might have seen, okay, this particular picture, which is on this. This particular picture is usually shown on the TDR of the tracker. And this has been done by the CMS artist, who is also the leader of the the first leader of the trigger group, who has made it. The reason I put it in, okay, because this particular picture is derived from a picture which was provided by the CMS simulation group when they had made the first version of the CMS tracker in the simulation code. So that is the contribution, one of the contribution of the CMS simulation to the CMS experiment. Now, this is the standard flow chart of a simulation that you start with a physics generators, which provides a particle for 4 vectors, and then they are fed into a code which is initiated by G4, and where you try to put in the geometry and material description of a given detector. This gives rise to something which is called hits. This is the interaction of the particles with the sensitive part of the detector. And then one has to go through this electronic simulation and produces the simulated raw data. After that, the simulated raw data behaves like the real data which comes from the detector, and they are treated identically in the system. So one key ingredient of the data analysis in HEP experiment is to understand the detector performance, estimation of the various efficiencies, to really look at the reducible and irreducible backgrounds, and determination of systematic uncertainties. And the most important tool for this is the detector simulation using inputs from some known physics events. So you have to know both your signals as well as your backgrounds. Simulation is also used to decide how the detector should be built. And that is where the beginning of the simulation code started. Now, the reliability of the Monte Carlo prediction depends on the goodness of the physics models of the event generator, obviously, and also a realistic description of the detector and quality of models used in evaluating the propagation of particles to the detector. So it's not just the detector simulation code is the important thing, also the goodness of the physics models is the event generator is also equally important. Now, what I have detailed here in this, first of all, is in the context of the CMS experiment. I've done only for the full simulation, starting from the first principle and with very little parameterization. That is the definition of full simulation. So I'm only talking about the full simulation part, and also only for the contribution to the making of the tool and not using the tool for any analysis, even including for the validation. So it's just the building of the thing. The CMS formally started in early 1990s. Okay, when, as Jim said yesterday, it was really started in 1992 with the AVR meeting. And the management at the time knew the importance of simulation, and they started the effort, which was led by these two gentlemen, Monte and Vico Karimaki. Both are Finnish guys, okay, and they were part of the U1 experiment, and they moved to this CMS and they started the simulation code. Soon, other groups also joined this activity and made the first version of a tool, which is called CMSIM1. This is based on the code of GN3, which was developed by essentially by a group of 5 people. Some of them may be known to you: René Brown, Francis Bruyère. I think it's Michel Mayer, Giannarini, and I forgot the 5th one. Okay, so this is a Fortran 77 based code, and using the Zebra as a tool, memory management tool. And it was a tool which was developed essentially for the left physics. Some of the early collaborators, mainly from the Paris institutes and from the Aleph, they chose a memory management package called BOSS. So CMSIM1 is based on GN3 and BOSS. Soon afterwards, okay, the US groups joined the effort, and there was a serious fight which began about which memory management package to be used. At the time, the software management was taken care of by Monte and Richard Mount. So one person was summoned to evaluate which way to go. And then one of the leaders from the UC Davis, Winston Coe, okay, invited myself and Vico to UC Davis to discuss this issue with the US expert, Uri Fischer. Now, incidentally, Uri Fischer was happened to be a member of EHS experiments. It is a European hybrid spectrometer experiment, which was where the architect for this experiment was Francis Bruyère. And he was also, Uri was an admirer of Francis, and also he was admirer of the software organization of L3. So that helped me a bit. So we thought, okay, the natural choice would be Zebra as a memory management package, so that we do not use multiple memory management package was necessary. And that's what CMSIM was born. Okay, so this is the CMSIM. I'm not calling it CMSIM2, rather than I'm calling it CMSIM, because that is the one which was used from then onwards. Now, this is just a picture of a CMS detector, just for the completeness of it. The main.
Can you increase your voice a little bit? Somehow it is a little lower.
Okay, I'm getting old and my voice is really going down, okay, with time. I do not know. Okay? I don't have a special speaker, okay, to talk to. Okay, I have to use.
There is, if I may suggest, in the settings for Zoom, you can artificially increase the gain for your microphone.
Okay. Okay. I think I'll try to speak louder, and hopefully that will work. So the main important thing is that though CMS has got several detector components, and each of the detectors has its own requirement. So we have to define a simulation package where we have a region-based optimization. So CMSIM really started as a GN3-based software written in Fortran 77. It relies on several detector experts. For tracker, it was Vico Karimaki. And then we have got ECAL, you have got Japia VL from, I think it's from Saclay, most likely. Shuichi Kunori for HCAL, Uri Fischer and Pedro Arce from the Mion system. My responsibility was toward the overall software and filling up the missing components, not the major detector components, but the other detectors. And obviously, okay, there are other things which are not a sensitive detector, but are required, like the beam pipe the magnet, the shielding, etc. So which really creates more background than signals. So CMC was a tool for not just detector simulation, but also for reconstruction. With the advent of C++, a part of the reconstruction code for the ecal was written in C++, and CMC became a hybrid system. I mean, it was mostly Fortran and partly C++. The CMC was used in writing the technical proposal of CMS, as well in the writing the technical design report for the major detector components like the magnet, which came first, then the hadron calorimeter, the muon detectors, electromagnetic calorimeter, tracker, trigger systems, and computing and software. I put this thing in this particular order, more from the chronological. The first EDR was a magnet, and then the other follows. The geometry of all major detector components was described in detail in CMS, and the future evolution of geometry description is derived from there. So I think the detector description in CMC was extremely important. Now, prior to collision, okay, I mean, to design any complex experiment relies on understanding the individual detector components, often with test beams. So one such activity happened during 1995-1996 with the hanging file structure of alternate layers of scintillator and absorbers in presence of magnetic field, either along the beam direction or perpendicular to the beam direction. Now, this is one of the pictures of this thing. You have got a module of electromagnetic calorimeter. This is just a prototype of some lead tungsten crystals, and then you have the hanging file structures, which comes in two boxes. Now, CMS learned from this test beam studied the effect of magnetic field in the potential end cap calorimeter, where the direction of the magnetic field is really perpendicular to the direction of the tiles, or in the barrel component, where the scintillators are more or less aligned with the magnetic field directions. So in one case, we have got only the scintillation brightness, and in the other case, you have got not just scintillation brightness, but also the increased path lengths because of the effect of the magnetic field for the low energy electrons which are produced. The standalone simulation code was the first written in Geon3, obviously, okay, because it was written in 95-96, but then it was rewritten in C++ and became the first contribution of the CMS collaboration to the Geon4 effort in the form of an advanced example. This advanced example is for composite calorimeter, and many users in high energy physics have benefited from uses of the composite calorimeter for their detector studies. As the knowledge of the future tracker grew, a more concrete proposal of the tracker geometry description was required. And this was done in a combined effort of 3 persons, Alexander Kanar, Ariana Frey, and myself. So all the components were described in detail: the wafer, the readout chip, the pitch adapter, the base plate, the supporting rods, cables, etc. So they are, first of all, described as components. So you can combine these components, okay, to make a module. For example, on the left side here, you have got the top module. It's a 2-layer. One is you can see the layer along the z-axis, and then there is a layer, okay, which is just underneath it, which is have a stereo angle of 100 milliradian with respect to this thing. Similarly, we have got a for the tech module. Okay, this has got a well, the basic thing is a rectangular parallelepiped. In the case of a tech module, okay, the wafers are in the form of a trapezoid, and then you have a pitch adapter here, followed by hybrid, and this is on a base plate. So that is how the module is first of all created. Then these modules are put together in the form of strings for tip, rods for the top, petals for the tech, and then you make the complete subdetectors, and finally the tracker. So it was, the whole idea for building this geometry was that you can take away only a part of it or the whole of it. And you can utilize that in a test beam atmosphere, or you can define it in the overall CMS system. The same thing followed for the pixel detectors as well. The pixel detector description, the barrel pixel was a product of the real detector I'm talking about now, not the CMS. The barrel pixel was a product of the PSI in Switzerland, whereas the forward pixel detector was a product of the US. So obviously, the first version of the barrel pixel was done by Danek, and the first version of the forward pixel was done by a couple of people working at Fermilab. I was involved in both of them, so that it will really get them with the correct orientation and get them integrated to CMS. Okay, so now the important thing is that this is one of my most favorite slides. The goodness of the geometry description was validated using the collision data. So the first test was to check the weights of the components and the combined system. Now this was done by really going with a chemical balance, to weigh the components of the real components, and also we try to have can compute the component as defined inside GN4, and we could really compare the weights, and we found out the weights have a near perfection thing. So it's not just a component. When the tracker was shipped to the P0.5, the weight of the entire tracker was taken along with the cables and everything, and then we again compared the thing, and we found out the things matched. That was the first comparison. The second, that means we are not just defining the tracker sensitive part, we are also defining the all the support system in a reasonably with the right density and so on and so forth. The second comparison was done from a study of the conversion vertices, the photons and nuclear interactions. And what you can see here, you have the comparison, the data versus Monte Carlo. And you can see that the height of the things for the data in Monte Carlo are matching very well. So they said, we have the right amount of matter described between the layers of the pixel detector as well as for the layers for the various components, like the different layers of the tips and something also for the tops. At the same time, some people was trying to see, how the particle masses are coming out. And they found out, the particle masses are coming out nicely for example, for the kaons and for the protons and antiprotons. But there was something in the data which is not coming out in the Monte Carlo. And we found out, that the reason for that is that the production of the deuterons were not in sometime by 1999 that we had the beta version of GN4, and it was jointly developed by a team from CERN and KEK. We started the activity in 1996, and the first beta version came in 1999. So CMS was a user for this beta version, and it was made the first prototype, which is called Oscar. And the three major players who took up this challenge were Isidro Gonzalez, Pedro Arce, and myself. It came in two versions. It has a standalone version which only tested simulation, and it has got no connection with the reconstruction code, which was developed as ORCA. This is basic work was done by Vincenzo and Stefan and a few others. So, but there was no connection at the time between the two. So it was essentially used, okay, to see that Gen4 can be used to do the simulation. But how good it is, okay, nobody knew. Then we have a combined version using the common tools from the reconstruction toolkit, which is called Cobra. And then both Oscar and Orca were developed to utilize Cobra codes to make the simulation and reconstruction code. And here are the comparisons of this thing for looking into the lateral and longitudinal shower profiles for the two versions of the Oscar. And I would say, okay, they matches, okay, with the two versions was coming two versions of Gen4 as well. Now, when Oscar and Orca were in the path of going to the final version, and this Jim has already mentioned about this. It started with the late arrival of the reconstruction code for the physics DDR. And this prompted an in-depth review of the CMS software. And I think Vincenzo and Lucia were summoned to Fermilab for this review, and I happened to be there at the time. And then I think there was a very severe criticism of the existing Orca code, and then they developed a new event data model, which was proposed by the Fermilab team, consisting of Mark Fischler, Chris Jones, Jim Kolkowski, Mark Paterno, Liz Sexton, Kevin Kennedy, and Bill Tannenbaum, and a few others. This was adopted, and the first version of CMS-SW was released. So when I have a first version of CMS-SW, obviously we need the simulation code. And this was, we have now a team of people who took care of the simulation code for the CMS-SW. And this team had Pedro, Tommaso Boccali, Fabio Cosuti, Tim Cox, Nicola Campani, Brian Hensley, Maya Stavinaku, and myself. It has got a coordination effort from Albert, Daniel, and Mike. So we require, okay, I mean, some geometry experts for the tool and not for the real description. This was developed by in-house by two persons, Michael Case and Martin Dendel, which is called Detector Description Language, DDD. And this was later on taken care of by Ian Osborne and Carl Gosalo. Now the Gen4 expert in this team is Vladimir Ivanchenko, and I'm maybe missing names, so please excuse if some of the names are omitted from this list. For a brief period of time, two Gen4 experts, Hans-Peter Welisch and Simone Gianni, happen to be part of the CMS. Simone still is a part of CMS, but is taking care of the PPS. And Hans-Peter has left, I think, high energy physics altogether. But he was the real expert for the hadronic physics in Gen4 at the time. So CMS benefited a lot due to their insights of the Gen4 code. The code was optimized to consume less CPU time and memory. And the result is that we have a code which runs 8 times faster than the Atlas full simulation code. So we are in reasonably good shape as far as performance is concerned. Now, as I said before, okay, we had a pre-collision time. We had a test beam first. So we continued with this test beam first with the real prototypes of the CMS detector. So the calorimeter teams made a continuous effort in learning about electromagnetic and hadronic showers. So the major simulation effort went to describe the test beam setups. We have several test beam setups of the H2 beam lines, and also some test beam setup of the H4 beam lines are described within the CMS-SW. And the main thing is that CMS built a table to accommodate one NCAP, 2 barrel modules of HCal, and a corresponding structure of HO, plus a mock-up structure for the magnetic coil on top of it. This could be preceded by a module mimicking ECAL or a real EB supermodule. So this is a simulation of the 2002 setup. And this was done essentially by Daniel Elvira. And this is for the version for the 2004 setup. And you can see here you have the HCal barrel, HCal end cap. You have got the HO, and you have got the ECAL. A module okay, which is a 7x7 module okay, of the lead tungsten crystals. And then you have the also some of the detectors which are in the beamline. Now, this thing was moved to the 2006. This is a real detector. This is not. We did not really make a simulation of the entire thing, but we tried to simulate. Okay, I mean the super module which is here. This is the HB, and this is the back is the prototype for the HO and the magnet, and this is the things which is HE, and this is the table which is there. And the beam apparently comes in this direction, and it goes to the ECAL, and then goes to almost to the corner between HB and HE. The goodness of this particular run is that we have a very special beam line, so that we can go down to energy of beam for 1 GeV. The reason, the specialty is that, okay, I mean, if you have a long beam line, okay, I mean, then the pi minus or pi plus which are produced from the secondary interaction, they will almost all decay to muons when it arrives to this setup. So they have to bring in a tertiary target to make a tertiary beam, okay, I mean, of either positive or negative beam. And then those beams, okay, will arrive the detector almost with a, well, I think relatively pure. Okay, but the 1 GeV beam was again, okay, for ion is essentially muons, but the 2 GeV onwards, okay, we have a good setting of the ions, kaons, and protons or antiprotons, depending on the charge of the beam. So we could really scan from 2 GeV to about 350 GeV, and can measure the what you call the energy from the thing. This is for all events, and this is for what the event is a MIP in ECAL. One thing you notice, okay, from this is that our calorimeter, the combined calorimeter, or just HCal. This is the combined calorimeter, and this is just HCal. Neither of them is a linear device. It has got a very large momentum dependence. So this is one thing which Jim was mentioning, but Jim said that we cannot have a linear device, okay, when you put in a crystal calorimeter in front of it. As soon as you have a crystal calorimeter in front of it, the so-called E over pi is about 4 to 5. And even if you have E over pi around 1, okay, in the HCal, okay, I mean, that cannot bring the linearity down. Okay, so that's a real problem of a composite calorimeter. You really cannot have a linear calorimetry in the system. So what we learned from the test beam. First of all, Gianfor came up with 2 major physics lists to describe the hadronic showers. The first one was called LHEP. Okay, this is the low energy, high energy, I think, parameterized beam, a parameterized physics list. This is a parameterized model based on the Gaussian code due to Humphreys-Feld of Aachen. And then it starts with another one, which is called a quark-gluon string model. And this is as a better theoretical insight. So I think the Gianfor people, okay, were essentially pushing for the KGSP model. But when we try to put that thing in and compare with the data sits here, LHEP is here, and KGSP is here. So it was trying to give much more energy than what is expected. So confronted with the data, KGSP model needed 2 serious extensions. First of all, at low energies, that means energies below about 15 or 20 GeV, QGSP has to rely on a cascade model due to Bertini. I mean, that was a model which was developed during what we call the wartime, when the by the nuclear physicists, okay, who build this particular model, okay, to describe uh, the low energy nuclear physics things inside it. And so this is one of the things which has to be introduced. And it also says, okay, it is required to introduce the effect of the saturation in producing scintillation light, often called as bulk correction for both crystals and plastic components. Now that was a real fight, okay, with the ECAL group, okay, for when we tried to suggest that. So there was a task force, okay, I mean, by the constituted by Jim at that time, which wanted to investigate the goodness of the CMS simulation software. And we had Seema, Suhadip, and myself, okay, from India, and then we have Shuichi, Stefan. These are the two essential guys, okay, for looking into the full simulation. There were other guys who were looking into the parameterization and things like that. But these are the full simulation guys looking into the full sim. We examined the lateral and longitudinal sharp profiles and learned a bit for the large energy deposition in ECAL. So here you have got the, after incorporating the Bartini cascade code and making a physics list called QGSP Bartini, and which uses essentially three models: QGSP at high energy, Bartini as low energy, and an intermediate energy is joined by the LAP, the low energy model, low energy parameterization of the Humphreys-Feld code. So that is the QGSP Bartini model, and you could see, okay, I mean, we have a reasonable agreement with the data. And the same thing is true, okay, I mean, when you have the QGSP Bartini model, okay, for the lateral sharp profile, we also get reasonably good agreement with the data. This is the 2004 test stream data, not 2006. And our choice, and this was also the PhD thesis of Seema. So I think, okay, I mean, well, I think she did also, after the PhD, also she worked in this task force as well. Now, another important thing which you learned, but it was ignored by the ECAL guys, that we have sometimes, not very rare, okay, this is the ECAL energy, is about HCAL energy. We have large energies in ECAL with very little energies in HCAL. And this large energy, okay, this is a 50 GeV pion, and we are getting more like 100 GeV and even up to 200 GeV in the ECAL. So our choice was the physics list, QGSP, FTFP BART, where the LEP part of the QGSP BART was changed by FTFP model, okay, which is becoming available at that time, and the use of Bark's law. And as mentioned, that we had a real tough time in convincing the ECAL guys that Bark's law is required, because ECAL is not just calorimetry for electrons and photons. ECAL is also used for energy measurements of hadrons, and unless you have the Bark's law, you cannot really describe the energy deposited by hadrons. So if you measure the energy of the jets, the Bark's law is important. And we are concerned about this, okay? But this was again ignored by the ECAL guys at that time. But it came back to us, not to the task, that particular task force, but it came back to CMS during 2010, when the energy of the LAC moved from 2 TeV to 7 TeV. We found out two things. We found out long tail at the high energy for the energy measurement in ECAL. You could see this is the black points as data, and the model is somewhere over here. So I think there was the black points and the model cannot explain each other. We have a large excess, okay, at the high energy. The second thing is that when you look at the missing and transverse energy measured in the calorimeter, again we have got problems. We have got something with some rare events, but it is not that rare that you can ignore them. We had the data has got large missing transverse energy, whereas the Monte Carlo is truncated, okay, I mean, somewhere here, okay, 50 to 100 GB. So the story for the ECAL, we have an anomalously large signals were observed in the ECAL with the appearance of very large energy deposits in a single crystal. These crystals are uniformly distributed in the barrel part of the detector, which uses APD, and they are not seen in the end cap crystals, which are read out using the vacuum photodiodes. So one of the things which CMS did to cut down the cost, at the end of, well, at the back of each crystal, we had got 2 APDs, but they did not want to have electronics for the 2 APDs. So they combined the 2 APDs in the readout system, and they have a single readout by combining the 2 APDs. So we have no idea what each individual APD has seen. The next thing is that the rise time of the electronic pulse is of this anomalous signal is consistent with an instantaneous signal from the APD, not the typical decay spectrum of the crystal. The rate is roughly proportional to the minimum bias type, and they are not observed during the cosmic reruns, but only during the collision and in the test beam runs with the incident hadron beams. The simulation code was changed to treat, so we had to something on hand. So we had to modify this geometry of the ECAL. We separately describe the APD volumes, and their APDs and the crystals are treated as independent detectors and with different energy against each of the system. Then we saw the simulated rate of the energy deposits in a single APD volume above a threshold match with the rate in the data. The simulation could also match the energy spectrum for the passage of single muons in the detector. We also matched the time distribution between data and the simulation. So it was concluded that anomalous hits are due to energy loss of heavily ionizing particles, protons or ions in the APD. And if we have 2 APDs rather than 1 APD, okay, it should have been seen in one of them and not in the other, whereas okay, a real signal should have been seen in both of them. So it would have been easy task for the ECAL guys later on, okay, to look at this particular noise. But obviously, okay, this was not done, okay, so they have to rely on something else. So one of the tools, okay, which was created was looking at what we call the look at the most energetic crystal and look the 4 crystals which are surrounding it, not the not the 8 crystals, but the 4 crystals, which is having a edge, not a vertex, common edge with the central crystal. And if you look at that, okay, then you look at the 1 minus E4 by E1 distribution. The standard simulation without the APD looks like this, where it ends. It has a peak at 0.883 or something like that, and then edges over there, whereas the data has also a sharp peak at 1. But once you have introduced this APD, you have got, you can describe this particular distribution pretty well. And when you put up this APDs in, you can match the energy distributions in the barrel also rather well, the time distribution rather well. So this is one of the things which we learned, which we should have learned from the testing, but we did not, but we could learn from the data and from the simulation of the ECAL barrel at that time. What about the missing energy distribution? Now, missing transverse energy is a key tool in the search of new particles in HEP. So I think many of the searches rely on the high MET values. So we have to somehow understand this large METs, which you cannot describe by the simulation. Now, this large energy was made was having this there, okay, where we have got large energy deposits in HF. And this large energy was seen in one type of fiber. You know, in HF, okay, we have the same ITA phi covered by two types of fibers. One is called long fibers, the other is called short fibers, to distinguish between the electromagnetic component of it. Now, we are seeing this thing is either long or short, but not in both. Again, okay, I mean, test beams saw this thing. Okay, I mean, when muons in the test beam gave rise to large pulses. And then we tried to take a look, okay, I mean, this particular things, okay, for the muon, this is from the test beam. And you could see that, okay, I mean, energy above 50 for 150 GeV muons, you could see, okay, I mean, the energies, okay, which is in the 200 GeV. And you can see at that time where exactly those ITA phi were there. And they're seeing that, okay, I mean, they where corresponds to ITA phi, where you have the PMTs at the back of it. Okay, I mean, it was basically the muons are hitting the PMTs. So again, okay, I mean, each PMT has a single anode. Okay, so we cannot really distinguish, okay, I mean, one from the other. So we took again, okay, help of the simulation to understand that. So we described the PMTs behind HF and declared the photocathodes as sensitivity detector. Also, the fiber bundles which move from the here all the way up to here, okay, going all the way to the PMTs, okay, they were described as well. So they're describing the geometry, and the hits in the fiber bundle are associated with a given readout channel. And obviously, the PMT hits are also described, goes to a given channel. So using these things, okay, together, we could really describe the anomalous hits are well reproduced in the simulation. And obviously, okay, we say, okay, I mean, this is really the either the punch-through or sell-throughs of the hadrons going all the way to the PMTs, or it could be the decay in flight for the hadrons to the muons, and the muons go through, okay, I mean, sell through to the PMTs. So that is the cause of this high energy things. So, so as a result, okay, I mean, what they did is that they replaced this. I think Suchand has already mentioned. They replaced this single anode PMTs with a what do you call 4 anode PMTs. There are 4 anodes in a given PMT, and 2 of these anodes, either 1,3 or 2,4, they are combined, okay, to give rise to the a readout system. So I think you have the 4 anodes, and each of the, for example, the long fibers are now read out with 2 anodes. The short fibers are read out with 2 anodes. So you have got redundant readouts, and using the redundant readouts, you can easily control the background. So that was an improvement, and that really takes care of the anomalies. Now, that goes as understanding the detector. Now, GN4 code is continuously developed, and CMS closely monitors those developments and utilizes the improvements on a regular basis. For example, there is an alternate geometry code which was developed in the sometime I forgot, maybe around 2016 or 2017, and which is called VecGeom. Okay, I mean, they wanted to have a vectorized code of a vectorized version of GN4, which never happened. But this particular code of called VecGeom was integrated to GN4, and we are the first users of this particular code for CMS simulation. So we did several things. We tried to see that we can utilize VecGeom with CMSSW. That was the first, see the integration of the code. Then we looked at the physics predictions, which were examined. And here are few comparisons. This is the track efficiency between the code with and without VecGeom. This is the energies measurement in the ECAL NCAP. And this is a comparison of the 2006 test beam data in the barrel part of the detector compared with the version with and without vacuum. So in all cases, we found out, okay, I mean, the physics is perfect. There's no hitch in the physics. So look at the performance. And we found out, okay, this particular code improves the performance by about 10%. And 10% is a large number for people who are usually do okay for the computing. So I think, okay, I mean, this was thing which was adopted by CMS a long time ago. And we're trying to see other improvements, okay, which is coming up from GN4. So we monitor the versions of the GN4 almost on a regular basis. Every month, okay, we have new reference versions of GN4, and we monitor those versions of GN4 as well. Now, any detector which is a static is dead. So CMS detector is not a static object. It has evolved over the years. So during LS1, the beam pipe was changed in view of the modified pixel detector. Of course, the modified pixel detector did not come immediately afterwards. Okay, it came in one of the year-ending technical stop. So, but the beam pipe was modified to come in the time of LS1. We had some of the beam scintillas which is removed. We tried to have the beam halo monitors and pixel luminosity monitors were introduced. Then the PMTs of HF were replaced with a new set. HO readout system was changed from the use of HPDs to SIPM. And totem and castor detectors were either decommissioned, I mean, either at that time or partly during the run-to period. So this was the activity during LS. After LS1, HF readout was modified to have a single cell being read out twice. That's what I just explained a few minutes ago. We have a new pixel detector with both barrel and end cap. We have the readout box of the HE started using SIPM, and the number of test segments was significantly modified. We have some demonstration chambers in the first layer of the GEM detector in 2017. And during LS2, some more changes are foreseen. We have the readout boxes of the HB also use SIPM and have more depth segments. The first station of GEM detector is now complete. Okay, we have now no longer just a demonstration chamber, but we have all the chambers of the GEM okay, are there in G11. We have a demonstration chamber for the G21 and also demonstration chamber from our for the forward backward RPC detectors in the stations 3 and 4. We have a new beam pipe and a shielding structure, and we have a new detector in the position of totem T2. So I think we have as you see, okay, I mean, it was a continuous improvement of the CMS detectors, and large part of these changes have been taken care of by myself. So that is for what's up to the present. What is about futures? So many detector elements will be unusable due to high luminosity runs of the LSC. Some detectors are changed due to damage due to radiation. As I said, okay, I mean, even now, okay, I mean, some of the layers of the EE is almost back, and some detectors will suffer due to very high occupancy rate. So a major change is foreseen in the CMS detector. This has been to some extent described by Kuchandra. We have a new tracker. We have the barrel calorimeter. Both ECAL and HCAL will have new electronics to extract timing information with much better resolution. We have introducing timing detectors both in the barrel and end cap to provide precise timing information with high precision. And so we have now not just 3-dimensional information, but a 4-dimensional information for every hit. The muon detectors will improve the solid angle coverage by completing the second and the 0th GEM station, the so-called G0 and G2. And the detectors are the lowest rings in the 3rd and 4th RPC stations. The N-cap calorimeter, both ecal and H-cal system will be replaced by high granularity calorimeter utilizing silicon and scintillation detectors. So Indian groups are participating in the simulation software for the future detector. For example, Shubhira and Shuchandra are modifying the digitization code for all components of the new tracker, including pile-up and premixing. Shuchandra did describe the simulation of the tracker testing facility in Day2. Simulation of the HDCAL test beam setup has been done by Shilpi and Ashim. Simulation of the HDCAL system is done by Prithvi. And simulation of the new muon detectors will be also is partially done by me. So detector simulation, I try to show that detector simulation of CMS is a rather long project, okay, but it is also complex. It needs good liaison with the detector integration team and also with the tool makers, which is Gianflow. So far, India has made a significant contribution to this project, almost from the conception, not right from the conception, but almost from the conception till now. I hope this tradition can continue in future. Thank you very much.
Thank you very much for this very comprehensive talk. And I also particularly enjoyed looking at the history of how it all got started. So do we have questions? Yes, Arnab, go ahead, please.
Hello, can you hear me?
Yes.
So my question is, I mean, like for the detector simulation, it's like there is always an interplay between the accuracy and the timing that it takes. And in the next phase of LHC, I mean, in phase 2, it will be more granular than before. So how do you think it will challenge the simulation?
Well, I think there are two things. Okay, I mean, phase 2 is complex for something else. Phase 2 utilizes HGCAL, for example, and HGCAL requires a much more detailed electromagnetic physics model than what is used in CMS simulation today. And once you employ that, the timing goes up by 50%. Now with the new detector, with the new tracker and the new HGCAL and all the MTDs and all that stuff, for the modified geometry, the simulation time goes up by a factor of 2, and new physics list gives another factor of 1.5. So we are getting physics list, okay, physics CPU time requirement of a factor of 3 higher. So this has been, I mean, one of the things, okay, where we are monitoring the performance, we are monitoring not just the performance of the run 3 geometry, but we are also monitoring the performance of the run 4 geometry. And the software team knows, okay, this particular aspect. So there are two things which we are trying to do. First of all, CMS is seeing, okay, I mean, can this be accommodated with the budget they have? And can we improve the timing somehow by cutting down certain things, okay, in the process? We are trying to do both, and we'll see, okay, I mean, how we eventually get. So it will not come as a shock to the CMS, because the CMS already has been shocked by this. Okay. And I see, okay, I mean, if we can get something better than what it is today.
Okay. Okay. And the other thing that I wanted to know is, you have been involved in many detector simulations. So it's, I think, a good time to ask you that which one was like your favorite and why?
look, I would always say, okay, I mean, something which has been proven by data is my favorite. So far, okay, the only thing which has been proven by data is, well, I would say, okay, I mean, many things have been proven by data. The tracker has been proven by data. The calorimeter system has been proven by data. The existing calorimeter system has been proven by data. So I cannot really say, okay, which is my favorite between the two, okay, but and certainly when EduCal will be proven by data, okay, I mean, I'll say, okay, I mean, that would be also would be a favorite thing to do, okay, but I may not live that long, okay, to see that is proven by data.
Okay. Okay, thank you.
Okay, thank you very much. I think we have a comment from the room, Kajal. Are you there? Okay, we circle back to you. Rajiv, would you like to make your comment?
Yeah, I actually had a question. Can you go back to that slide, Shananda, where you showed Bertini cascade model getting included? Yeah, so this actually is a quark gluon string model, and then you are extending it using this Bertini cascade model at low energies. So the two subparts of the question, one is how low is low, and secondly, is that somehow a statement that quarks and gluons are not felt at that particular point and only hadrons are seen? I mean, is there some kind of a physics there why you cannot use the QGSP and you have to go to the Bertini cascade?
Well, the thing is, okay, I mean, first of all, okay, I mean, Bertini cascade is one of the things which is there. Okay, I mean, the way the physics list is constructed by defining what do you call it, an energy region where a particular model is active, is good. The so-called quark-gluon string model, okay, they say, okay, I mean, it'd be good above 20 dB. And so in the past, okay, what they had is that at the low energy part, when they had the so-called QGSP physics list, and the low energy part was done by the LEP model. So it was a combination of the LEP and QGS model, which was doing that. Now, you cannot do the low energy part with a just with the same assumptions, but what is done in the quark-gluon string model. You have to do something more, okay, for the hybridization part and things like that. But even that thing is not enough, because you have to incorporate, okay, the evaporation, all the nuclear effect, okay, at the very low energies. The evaporation, the binding energies and things like that, okay, at the low energies, okay, I mean, which is very, very important. And they are, those particular effects were described at the time of bomb making. And so I think, okay, I mean, that's where the Bertini cascade code really originated from. Okay, I mean, the original Bertini cascade. Obviously, we are not using the original Bertini cascade, but some modified version of that, essentially coming from that. And so I think in the case right now, QGSP, FTFP, Bertini, QGSP is QGS part is valid from 20 GB onward. I think 8 GB to 20 GB maybe. 8 GB to 30 GB is for the FTFP part, and 0 to 12 GB is for the Bertini. So between 8 to 12 GB, you have got two active models, Bertini cascade and FTFP, and from 20 to 30, you have again got two active models, which is FTFP and QGSP. So what is being done is that when we are in some intermediate energy, okay, I mean, obviously a good fraction of those interactions will go into the QGSP and a good fraction at FTFP. And this is done essentially with using a linear extrapolation between the two energies. So at 20 GeV, at 20 GeV, it is all FTFP. At 30 GeV, it is all TGS. And between 20 and 30, okay, I mean, depending on where you are, at 25 GeV, for example, you have got equal mixtures of 50% probability it is QGSP and 50% probability is FTFP, and so on and so forth. So the same thing is done at the low energy side as well.
So this is rather ad hoc in the sense that there is no underlying theory connection with anything.
No, obviously not. Okay? I mean, this is one thing about the strong interaction. Okay, we cannot describe the data by a single model. At high energies you can, but at low energy you cannot.
No, but there are not even separated regions in the sense that there is an overlapping region where you need both.
Yeah, otherwise you have an abrupt thing. Okay, that's why, okay, I mean, you have to do that. Okay, you made a transition right at the thing. Okay, so you see where, up to what energy, okay, a particular model is valid, and you don't need a abrupt change, okay, from one model to another. So that's why we need a continuous transition.
Okay, thank you.
Great, thanks. Shubhankar?
Can you hear me?
Yes, we can.
Okay, Shunanda, the question is the simulation, is there any plan of moving to heterogeneous architectures in the future? Running it on heterogeneous platforms?
Oh yeah, I think I think there has been an effort to come in to see, okay, where GN4 can work. First of all, they tried vectorization, and that particular thing did not really well. I think we saw a factor of 2 improvement, okay, going from so-called GN4 to GNB in performance, but most of this performance improvement was essentially not in the vectorization part, but in improving something which will be done even in the scalar version. So the vectorization part was abandoned, okay, so we only had a paper out of it, but no real vectorized code. Because I think when you try to go from GN4 to GNV, okay, I mean, the only physics processes which was translated was the electromagnetic part. The hadronic part is too complex to be translated, so we tested only the electromagnetic part, and try to see, okay, I mean, is this bird file to translate the hadronic part? Obviously, the guys who were supposed to do the hadronic part, they said, no, there is no point of doing it. So the whole thing was closed. Now, obviously, okay, the next step is going to this, what do you call this, exascale computing. And there have been 2 activities, one centered in CERN and one is centered in US. We're trying to see, okay, I mean, when we try to go in for those activities as well. I think it's too early to say, okay, I mean, if it is how good it would be, but things do good, okay, I mean, I would say so. So maybe, okay, I mean, exascale computing it will be there in future, but at what time scale I really do not know. Obviously not in round 3 time scale. Maybe, okay, I mean, at round 4 time scale.
Thank you.
Yeah, Manas?
Yeah, can you hear me?
No.
Yes.
Yeah. At one point you mentioned that Atlas simulation was taking almost factor of 8 time compared to CMS. Why do you think they were lagging or not efficient? And what is the current status if you compare it, if simulation time for CMS event and Atlas event?
I think it's still a factor of 8 right now. There are two things, okay, why Atlas is less performant. First of all, okay, when we do some shortcuts, for example, when you have a neutrino, okay, I mean, which is produced in the process, we do not track the neutrino anymore, okay, I mean, so we stop the neutrino right there. So that is one of the shortcuts. We have something which is called Russian relay, which is applicable to photons and neutrons of low energy. And what is done is that when low energy neutrons below a certain energy is produced, we some of the times we just kill them there and we give a certain weight to the track itself. So that thing works. Okay, I mean, but that particular what you call it's obviously basically playing a relay in doing that. That works. Okay, for I think with some combination of the energy threshold, some combination of the probability, and things like that. Okay, and so this has to be carefully tuned, and this has been done for CMS, and we have been having that, okay, for most of run 2 simulation, not in run 1. So this is a second thing which we are using. The third thing which we are using is that when you go to very forward detectors like HF or even Castor, when you had it in the past, we see that we do not need a full simulation at that time. We have a frozen shower library and we substitute the shower library code in there. So these are the tricks, okay, which we have been using, okay, in our full simulation to make it faster. And this have that, okay, almost from the beginning. For example, shower code, I mean, inhibiting the neutrinos to be tracked. Okay, they are the things, okay, which were done in the beginning. Now, this is one part of the thing. The other part is that the calorimeter, the electromagnetic calorimeter of Atlas is really complex. It has a structure like a piano accordion, and in the accordion structure, placing a shower in an accordion structure is not easy at all. So that is the place, okay, where with the accordion structure geometry, okay, which is good for the physics, I think they have to spend enough time, okay, for simulating in the accordion structure. So this has to live with them. Okay, I mean, they cannot just throw away that their electromagnetic calorimeter. They have to live with their electromagnetic calorimeter, and they have to be penalized, okay, for using that in the simulation code. But that is a bad thing for the simulation. But the good thing is that they're even with a lower energy resolution in the electromagnetic calorimeter, they do better, far better than CMS, because their directional capability of reconstructing electron and photon is much better, which we do not have. We have a single measurement in the ecal for photon, and we do not have the position. I mean, we have to assume where the photon comes from, and that is not necessarily always correct. So I think, okay, I mean, you win some, you lose some. Okay, I mean, in the process, okay, you have a real detector where you win. You have a simulation where you lose. So that's where Atlas is. Now, Atlas is improving the simulation code. Okay, I mean, because we have been comparing our performance regularly between the two, and Atlas knows, okay, where they can improve their code, and maybe, okay, I mean, they will come up with a significant improvement, maybe almost a factor of 2 improvement and then we come much closer.
Just one supplementary question. I mean, CMS has a lot more material in the detector compared to Atlas. And even after the improvement, this factor of 4 will be there. So I don't know. I mean, if that can be understood in terms of the structure of the code, or there any particular issue is there.
No. I think Atlas is a bigger detector. So you have to track a particle much longer in Atlas than in CMS. I have not really thought about that part. It's not the material which matters, okay? It's how long you have to track a particle that matters. But hardly very few particles really go into the muon system. Most of the particles are confined into the tracker and the front part of the calorimeter. And the other thing which we have done a good thing is in defining the way we have defined the magnetic field. We are using a caching in the magnetic field, so that also gives us a good handle, okay, for doing that. So we try to use several tricks, okay, I mean, when we're simulating. Yes.
Okay, great. Thank you. Kajiri, would you maybe attempt your question now again?
No, for the sake of time, I think we will just terminate. No, it's okay.
Okay, excellent. So thank you everybody for being here.
I have to just apologize to Kajiri. Kajiri asked me to talk about some things which I did not talk about. She asked me to talk about the radiation hardness studies which we did in TIFR long time ago, and also the simulation in context of the understanding the ecal performance, okay, in TIFR. As I said, okay, I mean, I'm not talking about the application of the simulation code, so that's why I refrain from doing that. And the only thing which I say about the radiation hardness studies, the main person, okay, I mean, who was initiated the radiation hardness study was not Prince, it was Dr. Raghavan, and with Dr. Raghavan, myself, and some of the students at that time, okay, who are now
I was a student.
Senior faculties, okay, I mean, who took part in the radiation hardness studies.
Great, thank you. So thank you again to all the speakers, and of course, thank you for all of you. Thank you to all of you for being here. So the conference begins again at 2:30 to talk about ML and more physics stuff. So see you all then.